On Jupiter's moon, Io, there lies a feature that has captured the attention of scientists since its discovery in 1979. This is Loki Patera, a massive volcanic caldera located at approximately 13 degrees Re N, 39 degrees W on Io's subjovian hemisphere. At a staggering 225 kilometers in diameter, Loki Patera is the largest volcanic caldera on Io's surface. This enormous geological feature was first observed by Voyager 1, which detailed its unique characteristics. Its floor undergoes periodic resurfacing every 400 to 600 days, a testament to the intense volcanic activity that shapes Io's surface. Io, composed primarily of rocky material, is perturbed in its orbit by other large satellites nearby, contributing to its geological dynamism. The level of activity seen at Loki Patera is similar to that of a superfast spreading mid-ocean ridge on Earth. This intense volcanism has made Loki Patera a significant feature on Io, continually monitored and studied by scientists for insights into the moon's geological history. This persistent lava lake is not just a static feature, it frequently erupts, creating dramatic hotspots that change Io's surface dramatically over time. Below freezing temperatures are found on Io, except at its active volcanic hotspots, where temperatures can reach over 1200 degrees Celsius. In fact, Loki Patera contains an active lava lake that frequently erupts, contributing to the dramatic changes on Io's surface. The presence of over 12 active volcanoes on Io, including Loki Patera, indicates the sheer scale and intensity of this volcanic activity. Volcanic plumes from these eruptions can extend up to 300 kilometers above Io's surface, making them visible even from Earth using powerful telescopes. This frequent and intense volcanism continually reshapes Io's surface, contributing to the dynamic nature of this Jovian moon. Understanding Io's intense volcanism begins with Jupiter, its immense gravitational pull, and the moon Io. Every 42 hours, as Io orbits this gas giant, it experiences a tug-of-war between Jupiter and its neighboring moons, Europa and Ganymede. This constant struggle shapes Io into an ellipse instead of a perfect sphere. This distortion, known as tidal bulging, creates variations in the moon's shape as great as 100 meters. As Io stretches and relaxes, the internal friction generates heat, a process called tidal heating. The volcanoes on Io, including the famed Loki Patera caldera, are a result of this relentless heating. While the surface isn't entirely molten, the constant release of heat drives these explosive eruptions. Jupiter's gravity tugs Io back into its regular orbit after each perturbation, allowing the cycle to repeat every 42 hours and 27 minutes. This continuous process of tidal bulging and heating keeps Io's volcanism active and shapes its dynamic surface. This relentless cycle has been going on for millions of years, continually reshaping Io's landscape. The heat generated from these tidal interactions is what makes Io one of the most geologically active bodies in our solar system. So, the next time you look up at Jupiter and its moons, remember that Io's fiery nature is a testament to the immense gravitational forces at play in our solar system. The intense heat signature and cyclic behavior observed in its eruptions are direct consequences of these magmatic dynamics, driving the volcanism that has come to define Io's fiery nature. And as we continue to explore these celestial phenomena, we gain a deeper understanding of the incredible forces that shape our universe. Turning our attention now to the Juno mission, which has provided us with unprecedented insights into the intricate dynamics of Io's volcanic activity. During close flybys, the Juno spacecraft has observed Loki Patera, one of the most prominent volcanic sites on Io. The observations made by Juno have given scientists a deeper understanding of the cyclic behavior and magma dynamics that drive the intense volcanism at Loki Patera. By studying these eruptions up close, researchers can better comprehend how Io's surface is shaped and reshaped over time. It's fascinating to consider that the observations made by Juno are part of a long line of missions that have contributed to our knowledge of Io's volcanic activity. Each mission builds upon the discoveries of its predecessors, offering us a more complete picture of this dynamic moon. The eruptions at Loki Patera are not mere events, they are dynamic processes that alter Io's surface dramatically. Molten lava flows from the caldera can travel up to 200 kilometers before solidifying, creating vast expanses of fresh terrain. Despite this intense volcanism, Io remains heavily cratered. The persistent lava flows and dramatic hotspots may temporarily smooth the surface, but they cannot entirely erase the evidence of Io's past impacts. This process of erosion and reshaping is a testament to the dynamic nature of Io. The persistent lava lake at Loki Patera plays a critical role in driving this constant transformation. This continuous cycle of erosion and renewal at Loki Patera highlights the interplay between Io's past and its ever-changing present. The persistent silicate lava lake at Loki Patera is not just a feature, it is a force that shapes Io's surface and defines its ongoing story of erosion and renewal. But as we look to the future, our understanding of Io's volcanic activity is set to deepen. NASA's Juno mission is currently providing invaluable data on Jupiter and its moons. However, many questions remain unanswered about Io's volcanic activity. Future studies will aim to understand the magma dynamics and how they influence these eruptions. As we continue to explore Io, the hope is that new missions will unveil more of this moon's unique features and their underlying mechanisms. This initial sighting marked a pivotal moment, revealing Io as one of the most unusual moons in our cosmic neighborhood. Before this, volcanic activity was only known on Earth, making Io's discovery a groundbreaking revelation. The sight of Io's fiery plumes rising from its surface challenged our understanding of the solar system and propelled new avenues of research. Io, named after one of Zeus's lovers in Greek mythology, is now recognized as the most volcanically active body in our solar system. This legacy underscores how explorations like Voyager continue to unveil wonders, reshaping our knowledge of the cosmos. And as we delve deeper into Io's mysteries, the hope is that future missions will uncover even more secrets about this extraordinary celestial body. The discovery of active volcanism on Io was a testament to our curiosity and the power of exploration in expanding the boundaries of what we know. Understanding Io's unique features and their underlying mechanisms is more than just uncovering scientific facts. It's about appreciating our place in the vast, ever-evolving universe around us. Io's lithosphere is estimated to be around 30 kilometers thick. This relatively thin layer provides an understanding of why Io experiences such intense volcanic activity. Major tectonic faults crisscross Io's surface. These fault lines act as conduits for magma, allowing it to move from the core to the surface and fuel the volcanic eruptions we observe. The interplay between Io's thin lithosphere and the tectonic faults creates a dynamic system that drives intense volcanic activity. This understanding helps us appreciate our place in the vast, ever-evolving universe around us. By exploring Io's lithosphere and tectonic structures, we can better understand how they support the extraordinary volcanism seen at Loki Patera. This structural framework not only shapes Io's surface, but also plays a key role in shaping our understanding of the universe's dynamic nature. Sulfur volatiles are particularly important in this process. As magma from Io's interior rises towards the surface, it carries with it significant amounts of sulfur and sulfur compounds. When this sulfur-rich magma reaches the surface, it erupts violently, spewing these volatiles into Io's atmosphere. The release of these sulfur compounds enhances the activity at Loki Patera. They contribute to the bright plumes that can extend hundreds of kilometers above Io's surface. These volatiles not only create a visually striking spectacle, but also influence the moon's thin atmosphere and contribute to its distinctive sulfur-rich environment. This process of sulfur volatiles being released from Io's interior and into its atmosphere is a key mechanism driving the intense activity observed at Loki Patera. Understanding these dynamics not only enhances our knowledge of Io, but also deepens our appreciation for the complex interplay between volcanism and atmosphere in extreme environments. This intricate dance between magma dynamics and sulfur compounds is a testament to the universe's dynamic nature and the marvels it holds. The dance of Io, Europa, and Ganymede around Jupiter is not a simple waltz, but a complex astronomical ballet. These three moons are locked in a unique gravitational resonance, where their orbital periods are related by simple whole numbers. This gravitational dance has profound effects on Io, the innermost of these three moons. The constant tug-of-war between Jupiter and its neighboring satellites causes Io to be pulled into an elliptical orbit. The shape of Io's orbit changes from a near-perfect circle to a stretched oval as it moves closer and further away from Jupiter. This orbital eccentricity leads to significant tidal forces acting on the moon. These tidal forces are not just a result of Jupiter's gravity, but also the combined gravitational influence of Europa and Ganymede. The constant tug from these neighboring moons contributes to Io's internal heating. The heat generated by this tidal pumping, known as tidal heating, is what drives Io's extreme volcanic activity. As Io approaches Jupiter in its elliptical orbit, the gravitational pull causes the moon to flex and stretch. This constant flexing releases a tremendous amount of heat energy, much like how rubbing your hands together generates warmth. Over time, this heat builds up inside Io and eventually finds its way to the surface. This constant dance between Io, Europa, and Ganymede is more than just a beautiful celestial show, it's a testament to the interconnectedness of our solar system. It reminds us that even in the vast expanse of space, nothing happens in isolation. The forces at play are intricately woven together, creating the marvels we observe from afar. And as Loki Patera continues its rhythm of eruptions, it serves as a potent symbol of this grand cosmic dance, a vivid reminder that the universe is a place where even the most minuscule changes can have profound effects. While Earth and Io share the cosmic dance of volcanic activity, they do so in strikingly different ways. On Earth, our eruptions are primarily driven by the movement of tectonic plates, whereas Io's volcanoes seem to be fueled by the intense tidal forces exerted by Jupiter. This comparative volcanology reveals how even similar processes can yield vastly different outcomes in the cosmic ballet. The magma composition on Io is notably different from that of Earth. On our planet, magma is typically basaltic or silicic, containing high levels of iron and magnesium. In contrast, Io's volcanoes spew forth sulfurous lava, a direct result of the intense tidal heating the moon experiences. On Earth, our lava flows tend to be more silicic and viscous, leading to thicker, slower-moving rivers of magma. These differences in composition and viscosity lead to stark contrasts in how the two worlds' volcanoes shape their surfaces over time. While both worlds are subject to the same cosmic forces, their unique conditions create distinct expressions of volcanism. Earth's volcanoes often form dramatic conical peaks and deep calderas, whereas Io's eruptions can produce sprawling lava flows and vast caldera like that at Loki Patera. The volcanism on Io serves as a stark reminder of the varied and often unexpected outcomes of cosmic processes across our solar system. Looking at Loki Patera, we are confronted with a vivid example of how the grand dance of celestial bodies can lead to such profound and beautiful outcomes. Io is not a static body. It's pulled and tugged by the mighty gravity of Jupiter, its neighboring moons, Europa and Ganymede, and even by the Sun itself. This complex dance causes tidal bulging on Io's surface, as much as 100 meters in some areas. These internal movements create slight changes in Io's gravitational field, subtle but detectable shifts that scientists can measure using precise instruments aboard spacecraft like NASA's Juno. Imagine the Moon, just 1/6 the size of Earth, causing noticeable tides on our planet. Io's volcanic activity can similarly alter its gravitational field, enough to be measured from space. Understanding these changes helps scientists paint a more accurate picture of Io's interior. It's not just a static rock, it's a dynamic world constantly reshaped by the fire within. These insights into Io's gravitational field and internal structure demonstrate how Loki Patera influences not just Io's surface, but its very core. It's a testament to the profound ways celestial bodies can shape each other from within. The volcanic plumes from Loki Patera rise up to 300 kilometers above the Moon's surface, interacting with its thin atmosphere composed primarily of sulfur dioxide. These plumes are not merely spectacular displays, they have profound implications for Io's atmospheric chemistry. The interaction between the lava lake and the sulfur-rich atmosphere creates a dynamic interplay. As the lava erupts, it carries with it volatile compounds like sulfur dioxide, which then mix with Io's atmosphere. This process drives a continual cycle of atmospheric modification, where the volcanic plumes release substantial amounts of sulfur and other compounds into the environment. The result is a complex atmospheric chemistry that reflects Io's relentless volcanic activity. It's a testament to how interconnected these processes are, with each eruption leaving its mark on the Moon's atmosphere. This constant infusion of volatiles means that Io's atmosphere is far more dynamic than it might initially appear, given its thin nature. Scientists observe how these plumes behave and interact with the environment over time, offering valuable insights into the cyclic behavior of Io's volcanism. The plumes not only contribute to atmospheric chemistry, but also influence the broader environment, affecting how light and other wavelengths are absorbed and scattered within Io's atmosphere. Through these interactions, Loki Patera's activity continuously modifies Io's atmosphere, contributing to its complex volcanic processes. It's a vivid example of how celestial bodies can shape each other from within. This interplay between the lava lake and the atmosphere shows that Io is far from static. It's an ever-evolving landscape shaped by its own intense volcanism. As magma churns beneath Io's crust, it generates intense heat that drives Loki Patera's volcanic activity. This volcanism is so powerful that it affects Io's induced magnetic field, causing fluctuations and anomalies. Io's sulfurous atmosphere plays a crucial role in this interaction. The sulfur dioxide in Io's thin atmosphere interacts with charged particles from Jupiter's magnetosphere. This interaction creates a plasma torus around Io, a donut-shaped cloud of charged particles. The plasma torus extends far beyond Io's surface and influences Jupiter's magnetic field. The constant reshaping of Io's surface by Loki Patera's eruptions means that the Moon is never static. These eruptions not only shape Io's surface, but also contribute to the Moon's induced magnetic field. Understanding this complex interplay is key to unraveling the broader dynamics of Jupiter's magnetosphere. The extreme conditions within Loki Patera, temperatures reaching over 1700 DC, and magma dynamics shaping its surface mirror, those of Earth's most volcanically active regions. This makes Io an intriguing target for astrobiological studies. By exploring Loki Patera, scientists can gain insights into extremophiles, organisms capable of thriving in harsh environments. Understanding how life can adapt to such extreme conditions could help in searching for signs of life beyond Earth. Loki Patera's volcanic activity is cyclical, driven by tidal forces from Jupiter and the gravitational influence of Europa and Ganymede. Studying this cycle can provide insights into how extremophiles survive and thrive in dynamic environments. The persistent heat from Loki Patera also contributes to the overall thermal emission of Io, making it a significant area of study for astrobiologists. Future missions aimed at exploring Io's habitability could revolutionize our understanding of extremophiles and the possibility of life beyond Earth. Loki Patera not only offers a window into Io's volatile past, but also holds keys to unraveling the broader dynamics of life in our cosmic neighborhood. At the heart of Io, Jupiter's most volcanically active moon, lies Loki Patera, an immense caldera that has reshaped Io's surface repeatedly over millennia. This persistent silicate lava lake plays a pivotal role in recycling Io's crustal materials, driving the geological cycle that defines Io's tumultuous surface evolution. This heat redistribution can have implications for Io's overall stability and geological cycle. The warmer regions around Loki Patera may experience altered tectonic activity, potentially leading to more frequent or intense volcanic episodes elsewhere on the Moon. In comparison, other calderas on Io produce much less thermal emission. While other features may contribute to Io's volcanism, none match the intensity and efficiency observed at Loki Patera. Io's volcanism is driven by tidal forces, primarily from Jupiter and its neighboring moons. These forces tug at Io's interior, generating heat that fuels the eruptions. This cyclic nature is driven by magma dynamics, where the movement and temperature changes of magma beneath the surface play a crucial role. Understanding Loki Patera within this broader context helps explain why it stands out as one of Io's most significant features. Despite its prominence, Loki Patera is just one piece in the larger puzzle of Io's global volcanism, influenced by tidal forces and magma dynamics. Jupiter's massive gravity constantly pulls at Io, causing a phenomenon known as tidal stresses. Imagine a thick rubber band being stretched in opposite directions by two heavy weights. As the weights pull harder, the band becomes thinner in the middle and thicker at the edges. The same thing happens to Io as it orbits Jupiter. Jupiter's gravity tugs at Io from one side, while the other Galilean moons, Europa and Ganymede, pull it in another direction. The constant gravitational tug-of-war causes Io's shape to change, generating friction within its core. Understanding these tidal stresses is key to grasping the persistent activity at Loki Patera. Every eruption and every volcanic hotspot on Io is a direct result of this celestial tug-of-war. This vast lake of molten rock is not just a passive feature, it plays a crucial role in shaping Io's surface. These sulfur compounds are more than just atmospheric filler. They contribute to the formation of Io's distinctive red and orange coloring. As the volcanic plumes from Loki Patera erupt, they carry with them not just lava, but also these sulfur compounds. This intense heat is not just a byproduct of eruptions. It is part of what drives the cyclic behavior and magma dynamics that fuel Io's volcanism. Understanding this complex interplay between heat, composition, and eruptions helps clarify why Loki Patera is such an active site on Io's surface. As we delve deeper into the mechanics of Io's surface composition and its role in volcanism, it becomes clear that every eruption on this celestial body is a testament to the intricate dance between heat, material, and time. On Io, the distribution of heat generated by its volcanic activity is both vast and intricate. While the eruptions themselves may be isolated events, their thermal impact extends far beyond the immediate vicinity. This heat redistribution is crucial for understanding Io's global tectonics and surface dynamics. These immense plumes are not merely a visual spectacle. They significantly influence the redistribution of heat across Io's surface. This thermal energy does not stay localized. Instead, it spreads across the surface, driving tectonic activity and shaping Io's landscape. The lava travels up to 200 kilometers before solidifying, akin to an internal heating system that pulses with each volcanic event. This process is not just about the immediate effect, it's about the continuous redistribution of heat that shapes Io's global tectonics. Understanding this intricate dance between heat, material, and time is key to grasping Io's ongoing volcanic spectacle. For a celestial body as active as Io, the redistribution of heat is more than just a byproduct, it's a fundamental driver of its ever-changing landscape. The persistent nature of this lava lake has profound effects on Io's geological development. This persistent activity contributes to the redistribution of heat across Io's surface. The constant reshaping of the surface at Loki Patera serves as a vivid example of how Io's landscape is continuously sculpted by its volcanic forces. Understanding the mechanisms behind this intense volcanic activity is crucial for unraveling the mysteries of Io's dynamic landscape. To understand this, we need to delve into Io's interior composition. Seismic studies have revealed that Io has a core, mantle, and crust, each layer playing a crucial role in its volcanic activity. The core of Io is composed primarily of iron and other heavy elements, similar to Earth's core. This dense inner layer helps maintain the Moon's gravitational balance. The heat generated in the mantle due to these gravitational interactions creates magma that drives Io's volcanic activity. This process is known as tidal pumping. The crust of Io, while thin compared to Earth, is still significant in managing the release of this heat. It is composed of various rock types and minerals that can withstand extreme conditions. When the magma from the mantle reaches the crust, it creates immense pressure, leading to eruptions through fissures and calderas, such as Loki Patera. Seismic studies have detected numerous quakes beneath Io's surface, indicating that magma is continually being pushed upwards from the mantle to the crust. This constant movement of magma explains why Io's volcanic activity never seems to cease. It is a testament to the powerful forces at work within the Moon. Understanding these mechanisms provides a deeper insight into the forces that sculpt Io's dynamic landscape. This persistent heat flow is not just a spectacle, it reveals Io's internal dynamics. These gravitational interactions cause Io to be stretched and compressed in its orbit. This tidal flexing generates heat within Io's core, which is then distributed across the Moon's surface. But it's not just Jupiter that influences Io's heat flow. Radiogenic decay, the slow breakdown of radioactive elements within Io's interior, also contributes to its internal heat. This process is continuous and steady, complementing the intermittent heating from tidal interactions. These lava flows not only cover old terrain, but also contribute to the formation of new mountains and plains, adding complexity to Io's dynamic surface. Over time, repeated eruptions from Loki Patera can lead to significant geological changes on Io's surface, including the reshaping of mountains and the creation of vast plains. For instance, the heat from these eruptions can cause nearby rock to melt, leading to the formation of new lava lakes or even the collapse of existing structures. These eruptions, driven by the intense tidal heating from Jupiter and Io's unique orbital dynamics, have significant implications for Io's surface. During these cycles, Loki Patera can release large amounts of heat and lava. These cycles influence Io's overall geological evolution by maintaining a dynamic surface that is constantly being reshaped. NASA's Juno mission has provided valuable insights into these cycles, showing how the intense heat and lava flow impact Io's surface over time. While we continue to learn more about these processes, one thing is clear: Loki Patera plays a critical role in shaping Io over time. The story of Io's volcanic cycles is far from over, with each eruption and resurfacing event adding another layer to the complex and dynamic nature of this extraordinary moon. Loki Patera's recurrent eruptions play a crucial role in shaping Io's geological landscape over time. Each volcanic outburst from Loki Patera covers vast areas of Io with fresh lava, transforming the surface with each event. This constant influx of new lava has a profound impact on Io's geological evolution, continually renewing and reconfiguring its surface features. The magma dynamics underlying Loki Patera's volcanism contribute significantly to these processes, influencing the frequency and intensity of eruptions. Over long periods, these recurrent volcanic events drive extensive geological changes on Io, creating a dynamic and ever-evolving surface. This cyclical activity not only resurfaces the lava lake, but also alters the overall composition and texture of Io's crust. The heat generated by these eruptions further contributes to the thermal stability of Io, ensuring that the surface remains active and volatile. In essence, Loki Patera's persistent volcanism is a driving force behind Io's geological evolution, shaping its landscape with each new eruption. As we continue to observe and study these phenomena, the profound impact of Loki Patera on Io's surface becomes increasingly clear. The geological evolution of Io is inextricably linked to the ceaseless activity at Loki Patera, making it a key player in the Moon's dynamic history. Understanding these processes offers valuable insights into the larger mechanisms shaping our solar system's diverse landscapes. Imagine a lake of molten rock. That's what the magma chamber beneath Loki Patera is like. The size and heat of this magma chamber can cause significant changes in Io's mantle, which in turn affects the Moon's lithosphere. As the magma chamber heats up and expands, it exerts pressure on Io's crust, causing the surface to bulge. This process is similar to how heating a pan of water can cause it to overflow, but on a planetary scale. These repeated cycles of heating and cooling, bulging and subsiding sculpt Io's surface over time. Loki Patera's intense volcanism is essentially reshaping the Moon from within, creating a dynamic landscape that continuously evolves. The lithosphere, Io's outermost layer, is particularly vulnerable to these fluctuations. It can fracture and crack under the stress, creating paths for the molten rock to escape, leading to spectacular eruptions that we observe from Earth. The volatile gases, primarily sulfur dioxide, or SO2, spew into the thin air, creating a pungent atmosphere that is unique in our solar system. This isn't just any atmosphere, it's a chemical concoction forged by Loki Patera's relentless activity. When Juno performed its close flybys of Io, it detected dramatic shifts in the composition of these gases. These changes aren't subtle, they are as dynamic as Io itself. These shifts in atmospheric composition aren't just a byproduct of Io's volcanism, they are a direct consequence of the magma dynamics that drive Loki Patera's explosive displays. Imagine the magma beneath Io's surface, surging and retreating like tides on Earth. As it rises and falls, so do the levels of sulfur dioxide in the atmosphere. The result is a breathing atmosphere that reflects the rhythm of Io's heart, deep within its molten core. And this isn't merely a curious phenomenon, it directly impacts the surface of Io. The sulfur dioxide from Loki Patera's eruptions condenses and falls back as snow, painting Io's surface with a distinctive red and yellow hue. Thus, Loki Patera doesn't just shape the surface, it also paints it with the very chemicals it spews into the air. This cyclic dance between Loki Patera's eruptions and Io's atmospheric composition creates a delicate balance that is uniquely Io. Juno's observations have revealed that Loki Patera's eruptions follow a predictable pattern. By understanding these cycles, we can better predict and appreciate the dynamic nature of Loki Patera's volcanic activity. This cyclic behavior offers valuable insights into the predictable, yet ever-changing landscape of Io. As we continue to study Loki Patera, we gain a deeper appreciation for the complex interplay between magma dynamics and Io's atmospheric processes. These episodic events are not random. They follow recurrence patterns that scientists have begun to decode. Magma dynamics play a critical role in influencing these patterns. The cyclic nature of these volcanic episodes suggests that there are predictable triggers. Understanding what drives these events can help in studying their effect on Io's surface over time. This understanding helps us predict the impact of these events on Io's surface and its long-term geological evolution. One of the key questions in understanding these dynamics is the potential role of subsurface water in fueling this intense volcanic activity. The presence of subsurface water could significantly influence magma generation and dynamics on Io. Water could lower the melting point of rock, making it easier for magma to form beneath the surface. By understanding this connection between water and volcanism, we deepen our comprehension of Io's internal processes and the mechanisms driving its intense heat. The heat flux from Loki Patera contributes significantly to Io's overall thermal anomalies. This persistent heat source ensures that the region around Loki Patera remains hotter than surrounding areas, creating distinct thermal patterns. These thermal anomalies are not just local phenomena. They have geological implications that ripple across Io's surface. The persistent heat can lead to the formation of new volcanic features and alter existing ones. Observations from NASA's Juno mission reveal that the heat distribution around Loki Patera is not uniform. There are patterns of temperature variations, suggesting complex interactions between Io's internal processes and its volcanic activity. Analyzing these patterns provides insights into how volcanism influences Io's surface features and overall thermal balance. The intense heat from Loki Patera reshapes the landscape, creating a dynamic interplay between Io's internal heat and its external environment. These insights into Io's heat distribution further our comprehension of the mechanisms driving its intense volcanism and the role these processes play in shaping Io's unique characteristics. Understanding this heat distribution reveals the extensive influence of volcanism on Io's surface features and overall thermal balance. It's a reminder that even in the most distant reaches of our solar system, powerful geological processes are at work. By examining the intricate balance of Io's heat distribution, we appreciate the profound impact volcanism has on shaping not just a moon, but an entire world. To truly grasp the extraordinary volcanic activity at Loki Patera, we must step back and consider the geological context of Io itself. Its intense heat and geological activity are driven by powerful forces that shape the moon's surface. At the heart of this geological dance lies a delicate balance between tidal forces and Io's own internal heating. Jupiter's gravitational pull constantly deforms Io, creating heat through tidal friction. This process, known as tidal heating, is the primary driver of Io's volcanism. But this heat is not evenly distributed across Io's surface. Instead, it is concentrated in volcanic hotspots, such as Loki Patera. As we dive deeper into Io's geological context, it becomes clear that Loki Patera is not an isolated phenomenon, but a key player in the moon's dynamic surface. By examining other volcanic centers on Io, such as Prometheus or Amirani, we see a similar pattern of intense activity driven by the same forces. Placing Loki Patera within this broader geological context highlights its role in shaping Io's surface and driving the moon's distinctive volcanic patterns. As the lava flows travel across Io's surface, they melt everything in their path. The intense heat from these eruptions also creates unique geological formations, such as calderas and lava tubes. Juno's observations have provided insights into these cyclic behaviors and the complex magma dynamics at play. This heat is not just a spectacle, it's the driving force behind Io's ever-changing surface. The persistent reshaping and melting of the surface create a dynamic landscape that is constantly evolving. Understanding this volcanic heat helps us appreciate the profound impact Loki Patera has on Io's surface dynamics. And as we gaze at these fiery eruptions from afar, we're reminded of the raw power that shapes our universe. These pyroclastic materials, formed from rapidly cooled lava and volcanic gases, blanket Io's surface, creating distinctive geological features. But what mechanisms drive these intense eruptions that create such significant pyroclastic deposits? This process causes Io to experience significant internal friction and heat generation, fueling its powerful volcanic activity. The resulting lava flows and pyroclastic eruptions not only create dramatic hotspots, but also contribute to Io's constant geological reshaping. With each episodic brightening event, Loki Patera's caldera is resurfaced, ensuring that Io's landscape remains ever-changing. And as we continue to observe and study these processes, we gain a deeper understanding of how our cosmic neighbors are shaped by the raw power of volcanism. In the vast canvas of Io's surface, Loki Patera stands as a testament to the unceasing geological transformation that defines this extraordinary moon. These episodic brightening events have been recorded as occurring roughly once a year, further underscoring the active nature of this geological hotspot. Despite its ferocious nature, studying Loki Patera's eruptions has provided valuable insights into the cyclic behavior and magma dynamics of Io's volcanism. Each eruption brings new insights, contributing to our understanding of Io's unique geological processes and the role they play in sculpting this extraordinary moon. Beneath the surface of Jupiter's moon, Io, something extraordinary is happening at Loki Patera. The heat from Loki Patera contributes to Io's overall thermal profile, making it one of the hottest bodies in our solar system. Magma dynamics are key to understanding these thermal anomalies. Heat from Loki Patera creates distinct hotspots on Io's surface, further shaping its unique thermal characteristics. Despite the extreme temperatures, these hotspots are not molten. Instead, they represent an intricate balance of heat and material being recycled through Io's volcanic processes. This persistent activity illuminates how Loki Patera drives Io's distinctive thermal characteristics, offering a deeper understanding of its intense volcanism. This constant tug-of-war heats up Io's interior, creating a vast network of magma chambers beneath the surface. The movement and interaction within these chambers contribute to the cyclic eruptions observed at Loki Patera. Recent findings from observational data suggest that magma dynamics also play a crucial role in triggering these eruptions. As magma rises and falls within the chambers, it can interact with different rock types, leading to variations in temperature and pressure. When magma reaches a critical point of instability, it forces its way through fissures and vents at Loki Patera, resulting in the dramatic eruptions that light up Io's surface. These volcanic triggers are not just fascinating phenomena, but also shape Io's distinctive thermal characteristics. By understanding these mechanisms, we gain a deeper insight into the intense volcanism that defines Loki Patera and Io's surface. As our knowledge of Io's volcanic triggers grows, so too does our appreciation for the dynamic nature of our universe. Each eruption at Loki Patera is a testament to the intricate dance of celestial mechanics that drive the cosmos. And with each new discovery, we take another step toward unraveling the mysteries of our solar system's most extraordinary worlds. Over time, these lava flows harden and build up layers of fresh material that cover the older surface. This recycling of material is a key component of Io's geological cycles. These periodic eruptions are not isolated incidents, but part of a larger cycle that involves both the creation and destruction of surface features. The erupted material doesn't just form new surfaces, but also contributes to the ongoing recycling of Io's crust. This understanding of geological cycles is crucial for comprehending how Io's landscape has evolved over time and will continue to evolve in the future. This understanding of how Loki Patera distributes volcanic heat across Io's surface is essential for comprehending the moon's geological cycles and its ongoing evolution. As we delve deeper into Io's secrets, the role of Loki Patera in distributing volcanic heat serves as a powerful reminder of the dynamic processes that sculpt our cosmic neighborhood. The repeated eruptions from this active site are so powerful that they can be detected from Earth, even with the vast distances involved. The heat from these eruptions plays a crucial role in Io's geological evolution, continually transforming the Moon's surface. Over long periods, the heat and material ejected from Loki Patera have contributed significantly to the formation of new crustal layers, making it a pivotal feature in Io's geological history. As we gaze at this celestial spectacle from afar, we are witnessing not just a momentary eruption, but the ongoing tale of Io's volcanic evolution. To understand the persistent, fiery display of Loki Patera, we must delve beneath Io's surface to explore the subsurface magma reservoirs that fuel this volcanic powerhouse. These reservoirs are vast chambers filled with molten rock, or magma, which lie deep within the Moon's crust. Imagine a chamber as large as a city block, but instead of concrete buildings and bustling streets, you have a churning mass of molten rock, a literal sea of fire. This is the reality beneath Io's surface. The magma in these reservoirs is constantly replenished from the core of Io by tidal heating. The gravitational pull of Jupiter and its nearby moons, Europa and Ganymede, cause Io to flex and stretch. This flexing generates heat within Io's interior, much like how a rubber band heats up when it is repeatedly stretched and released. The intense heat melts the rock beneath Io's surface, creating the magma that feeds into these reservoirs. Think of these reservoirs as massive, slow-motion pressure cookers, where molten rock is continuously heated and pressurized. Over time, the pressure builds until it forces its way to the surface in dramatic eruptions, the volcanic fireworks we see at Loki Patera. This cycle of heat generation, magma formation, and eruption is a fundamental mechanism driving Io's intense volcanic activity. Diving deeper into Io's volcanic dynamics, scientists have uncovered a critical factor influencing Loki Patera's eruptions: subsurface water. This interaction can lead to the formation of hydrothermal systems, where high-pressure steam is generated. By studying how subsurface water affects magma dynamics and eruptions, scientists can better understand the mechanisms driving Io's intense volcanism. The stability of this lava lake is vital, as it allows for sustained heat output and contributes significantly to Io's global heat flow. By unraveling these internal processes, researchers gain valuable insights into the complex dynamics governing Loki Patera's volcanic activity. These discoveries highlight the interconnected nature of Io's subsurface systems and their pivotal role in shaping the Moon's volcanic landscape. As our exploration continues, it becomes clear that Io's volcanism is a testament to the intricate and dynamic processes occurring beneath its surface. By understanding how subsurface water influences magma dynamics and eruptions, we gain a deeper appreciation for the cosmic ballet taking place on this volcanically active Moon. This insight provides a glimpse into the fundamental mechanisms that have sculpted Io's surface over eons and continue to shape its ever-changing landscape. Subsequent studies with more advanced instrumentation found that these eruptions are not uniform in intensity. Instead, they exhibit a dynamic pattern of peaks and troughs over time. The volcanic plumes from these eruptions extend up to 300 kilometers above Io's surface and can reach speeds of 1 kilometer per second, scattering material that contributes to the plasma torus around the Moon. This cyclic behavior over millennia has sculpted Io's ever-changing landscape, providing a temporal perspective on how Loki Patera shapes the surface of Jupiter's most volcanically active moon. It is through these eruption patterns that we can begin to understand the fundamental mechanisms that have shaped Io's surface over eons, continuing to reshape its dynamic geology even today. And perhaps that is just one more reminder of the immense forces and cycles at play in our cosmic neighborhood, continuously redefining the surfaces of the worlds that orbit around us. Scientists have observed that these eruptions can create new silicate minerals on Io's surface, which are not typically found in other parts of the Moon. The heat and fresh lava introduce elements and compounds not present elsewhere. Io, with its thin sulfur-rich atmosphere, experiences significant chemical reactions triggered by these eruptions. The high temperatures and the interaction of magma with the atmosphere can produce new and unique compounds. These geological processes driven by Loki Patera illustrate the broader impact of volcanism on Io's geology and evolution. The moon's surface is in a state of constant renewal, shaped by the forces deep within. The persistent lava lake impacts heat distribution across Io in several ways. Firstly, the constant presence of molten rock ensures that a significant portion of Io's surface remains heated even as other areas cool. This lava lake is not a static feature, but rather a dynamic component of Io's geological processes. This heating not only melts the surface, but also contributes to the replenishment of Loki Patera's magma reservoir. Another intriguing aspect is the potential role of subsurface water. Water can lower the melting point of silicate rocks significantly, facilitating magma generation and upwelling. The presence of water in Io's interior is supported by observations of hydrogen-rich plumes from the volcanoes. These plumes, detected during Juno's flybys, indicate that water is playing a crucial role in Io's volcanic processes. Through these insights, we can appreciate the intricate interplay between geological forces and the extraordinary volcanic activity on Jupiter's moon. As we continue to explore this cosmic ballet, each new discovery deepens our understanding of the universe's complex and awe-inspiring wonders. The fluctuations in heat flow also have implications for Io's internal structure. The periodic variations create stress points within the moon's crust, leading to a constant cycle of tectonic adjustments and volcanic activity. At the heart of Io's extraordinary geology lies its magma dynamics. Imagine a lava flow extending from the caldera of Loki Patera to a point nearly twice the length of the Grand Canyon. The sheer scale of these lava flows shapes Io's surface in profound ways. The volcano emits both effusive and explosive eruptions. Effusive eruptions produce long, fluid lava flows that sculpt the landscape over time. On the other hand, explosive eruptions release energy in powerful bursts. These events can eject material hundreds of kilometers into the air, creating dramatic and immediate changes to Io's surface. This duality in eruption types ensures that Io's surface is continuously reshaped by Loki Patera's activity. Such reshaping not only affects Io's physical appearance, but also plays a role in modifying the moon's thermal properties over time. As new lava covers older surfaces, it contributes to maintaining a uniform thermal distribution across Io. This dual role is essential for the survival of the many forms of life that depend on Io's thermal stability. Understanding Loki Patera's profound influence helps us appreciate the delicate balance and interconnectedness within Jupiter's intricate system. Silicate eruptions are characterized by their high viscosity and temperature, making the lava flows particularly dynamic. These flows sculpt distinctive channels and flow fields across Io's surface. The silicate composition of these lava flows plays a crucial role in their behavior and the formation of these features. As the molten rock cools, it creates complex geological patterns that are unique to Io's environment. One remarkable aspect is the speed at which these lava flows travel. Reaching velocities up to 1 kilometer per second, they shape Io's landscape rapidly and dramatically. These high-speed flows leave behind intricate networks of lava channels and flow fields that extend for hundreds of kilometers across Io's surface. These features are a testament to the immense energy and fluid dynamics at play. This ceaseless transformation offers a fascinating window into the complex interactions between Jupiter's gravitational influence and Io's internal magma dynamics. During each eruption, Loki Patera releases a cocktail of gases into Io's thin atmosphere. Sulfur dioxide is particularly prevalent, creating a distinctive yellow and orange hue across the moon's surface. But the story of Io's atmospheric composition doesn't end with sulfur dioxide alone. Observations by NASA's Juno spacecraft have revealed that Loki Patera also emits significant amounts of sulfur monoxide, or SO. This gas is particularly notable because it reacts with other compounds in the atmosphere to form complex sulfur compounds and aerosols. These sulfur compounds and aerosols not only influence the color of Io's atmosphere, but also play a critical role in its global climate system. They absorb sunlight and scatter light, affecting the moon's radiative balance and energy distribution, a process known as photochemistry. The gases released by Loki Patera and other active sites on Io create a complex interplay between the moon's surface and its atmosphere. This interplay drives the unique atmospheric conditions we observe today, conditions that are unlike any other in our solar system. Over decades, this persistent volcanic activity has profoundly reshaped the local geology around Loki Patera. The cycles of volcanic eruptions at Loki Patera demonstrate the long-term effects of persistent volcanism on Io's surface. Understanding these cycles provides insights into how Io's unique atmospheric conditions and geological features have evolved over time. It's not just the surface of Io that fascinates scientists. Below, something even more remarkable is at play. Imagine a lake so immense it could cover an area larger than the state of Ohio, yet it lies hidden beneath Io's surface. These reservoirs are not merely passive. They actively influence Io's volcanic activity by altering magma dynamics. Magma, the molten rock beneath Io's surface, can be dramatically affected when it comes into contact with water. As magma interacts with these subsurface reservoirs, it undergoes rapid changes in temperature and composition. This interaction can lead to explosive volcanic eruptions, the kind that have been observed at Loki Patera. The unique conditions on Io, driven by tidal heating from Jupiter's massive gravitational pull, create an environment where these interactions are frequent and intense. These subsurface water reservoirs help explain the cyclic behavior of Io's volcanism. At Loki Patera, where some of the most dramatic eruptions occur, these water-magma interactions are particularly evident. Pyroclastic flows are a rapid collection of hot gas and rock that explode from a volcano, creating fast-moving currents of ash, pumice, and other volcanic materials. These flows move at astonishing speeds, often exceeding hundreds of kilometers per hour. Observations from Juno and Voyager missions show that these flows have created vast lava fields across Io's sub-Jovian hemisphere. In comparison, Earth's volcanic processes are slower and more controlled. Here, lava flows move at speeds of only a few meters per hour. Io's intense tidal heating from Jupiter and the constant supply of lava from Loki Patera drive these rapid changes over time. As a result, Io's surface is in a state of constant renewal, with old features being erased and new ones formed repeatedly. These pyroclastic flows are a testament to the dynamic nature of volcanism and its profound impact on planetary surfaces. Io's unique position within Jupiter's gravitational pull subjects it to tremendous tidal forces, constantly squeezing and stretching the moon's surface. These tectonic stresses are the unseen hand that carves Io's volcanic landscape, shaping its surface as relentlessly as an artist's chisel. Juno's observations reveal that these stresses play a crucial role in the formation and movement of magma beneath Io's crust. This magma, generated by the relentless tidal forces, feeds the persistent lava lake and fuels its eruptions. It's a cycle as regular as the tides themselves. Tidal forces stretch Io's crust, magma forms, lava flows, and the surface is renewed. Understanding these tectonic movements deepens our grasp on how Io's unique internal structure fuels its volcanism and continually reshapes its surface. Perhaps most fascinating is that this dynamic dance of tectonic stresses and volcanic fire reveals Io's place within the grand ballet of the solar system's ever-evolving landscape. And so, Io continues its ceaseless tectonic waltz, a testament to the raw power of gravitational forces and the relentless cycle of renewal. Moreover, Loki Patera's role extends beyond immediate physical impacts. The frequent eruptions and heat releases contribute significantly to Io's global heat flow, potentially accounting for over 15% of the Moon's total thermal emissions. This highlights how Loki Patera serves as a key regulator in Io's complex thermal balance. Beneath Io's surface lies a complex interplay of tidal stresses and heat flow, contributing to an unusually thin lithosphere. These stresses, combined with the heat generated by Jupiter's gravitational tug, significantly thin Io's lithosphere. The intense heat generated by these processes enables molten lava to flow more readily, leading to frequent eruptions that shape Io's surface. This constant reshaping of the landscape is a stark reminder of the dynamic nature of Io's geology and the role that lithospheric thinning plays in its volcanism. Understanding these mechanisms deepens our appreciation for why Loki Patera is such an active and transformative force on Io's surface. Beneath Io's thin atmosphere, vast reservoirs of magma churn and boil. These magmatic dynamics are driven by the tidal forces exerted by Jupiter and its other large satellites. The magma beneath Loki Patera is particularly rich in sulfur compounds, a consequence of Io's unique volcanic environment. This sulfur-rich composition plays a crucial role in modulating the eruptions at Loki Patera. Sulfur compounds lower the melting point of the magma, making it easier to reach the surface. When these sulfur-laden eruptions occur, they release immense amounts of sulfur and sulfur compounds into Io's thin atmosphere. The constant rain of sulfur dioxide, SO2, from the eruptions contributes to the distinctive red, orange, and yellow hues on Io's surface. These magma oceans, which are part of the global mantle beneath Io's crust, contribute to a unique internal structure that supports the enduring volcanic activity seen at Loki Patera. Io's extensive magma oceans are thought to be a result of tidal heating from Jupiter and the gravitational interactions with other large satellites, such as Europa and Ganymede. This constant heat production allows for the formation and maintenance of magma oceans that can reach depths of over 120 kilometers. But why do these eruptions occur so frequently? The answer lies in the dynamic nature of Io's magma oceans, which constantly churn and move beneath the surface, driven by the intense tidal forces from Jupiter. Think of magma as a restless ocean, constantly moving and reshaping Io's surface. The formation of magma channels and hotspots is driven by these tectonic forces. Imagine two tectonic plates grinding against each other, creating friction that heats up magma below the surface. This intense heat drives the frequent and powerful eruptions at Loki Patera. Understanding these processes helps us grasp why Loki Patera erupts so frequently and how its volcanic behavior shapes Io's ever-changing surface. So, the next time you observe Io's volcanic fireworks, remember that beneath the surface, tectonic plate interactions are driving this incredible display of celestial pyrotechnics. When the lava lake erupts, it releases intense heat that travels through Io's rocky interior, cycling essential elements like sulfur and silicate. These eruptions contribute to the constant reshaping of Io's surface, creating a dynamic landscape where old materials are continually replaced by fresh lava. The cyclic behavior observed in Loki Patera's volcanism plays a critical role in influencing these geochemical cycles over long periods. Magma dynamics beneath the surface drive this intense volcanism, with magma chambers undergoing periodic replenishment and rejuvenation. Over time, these geochemical cycles contribute to the cyclic behavior of Io's volcanism, influencing both its surface evolution and chemical makeup. So, when you observe Io's fireworks from afar, remember that beneath the spectacle, Loki Patera's geochemical cycles are shaping this remarkable world. As Io continues its dance around Jupiter, driven by tidal forces and geochemical cycles, Loki Patera plays an essential role in maintaining this dynamic celestial ballet. To understand the persistent silicate lava lake, we must delve into the subsurface structures that feed it. Magma chambers and lava tubes form a vast network beneath Io's crust. These magma chambers, as large as the state of Hawaii, act as reservoirs for molten rock that periodically erupts onto Io's surface. By understanding this hidden geology, we see how Loki Patera's continuous eruptions shape Io's ever-changing surface. Each eruption reshapes the landscape, leaving behind a record of Io's fiery dance. As we gaze at Io from afar, remember that beneath its surface, an unseen orchestra of magma and lava is conducting a grand performance. This hidden dance shapes the celestial ballet of Loki Patera. And so, Io continues its dance around Jupiter, driven by tidal forces and the ceaseless cycle of eruptions that keep Loki Patera's surface ever-changing. Loki Patera's volcanic plumes release a cocktail of volatiles into Io's atmosphere. The most prominent of these are sulfur and sulfur dioxide. At such heights, the volcanic material can be carried by Io's tenuous winds and distributed across the moon's surface. This widespread dispersion of sulfur compounds plays a significant role in shaping Io's surface and atmosphere. The continuous cyclic behavior of Loki Patera ensures that these eruptions are a regular occurrence. Each eruption event releases a significant amount of heat and volatiles into the atmosphere. These periodic injections contribute to Io's unique pulsating heat signature. These currents generate magnetic fields that can be detected from afar. Spacecraft like Juno, equipped with sensitive instruments, have measured these localized magnetic anomalies. The data reveal intricate patterns, with variations in Io's magnetic field corresponding to Loki Patera's eruptive cycles. These studies remind us that Io is not just a distant celestial body, it's a dynamic, ever-changing world driven by powerful forces beneath its crust. As we continue to explore and analyze the data from spacecraft, our understanding of Io's magnetic field anomalies will deepen, adding another layer to the fascinating story of this volcanically active moon. This ongoing research into Loki Patera's influence on Io's magnetism not only expands our scientific knowledge, but also underscores the importance of studying volcanic activity in our solar system. The pulsating heat signature and magnetic anomalies together paint a vivid picture of Io's geological dynamism, a testament to the power hidden beneath its surface. Scientists can map temperature fluctuations at Loki Patera by analyzing the infrared emissions captured during spacecraft flybys. Using this data, they've identified hotspots that vary over time, with some areas reaching temperatures as high as 1700 degrees Celsius. These thermal anomalies illustrate the intense heat that periodically reshapes Io's surface. As Juno continues to gather more data, we gain a deeper understanding of how this persistent volcanic activity influences the moon's geological dynamics over decades. The persistent silicate lava lake and its role in shaping Io's surface highlight the enduring power of heat hidden beneath the moon's crust. Imagine Io as a planetary body with an interior similar to Earth's, but on a much smaller scale. This tiny world, about the size of our own moon, harbors something extraordinary: vast magma oceans that play a pivotal role in shaping its surface. These magma oceans are thought to be a consequence of Io's unique orbital dynamics and the tidal forces exerted by Jupiter, its parent planet. The constant tugging from Jupiter and other nearby moons creates friction within Io's mantle. This tidal flexing generates immense heat, which in turn melts large portions of Io's interior, creating these magma oceans. This process is known as tidal heating. This continual influx of magma ensures that volcanoes like those at Loki Patera remain active over geological timescales, shaping Eo's surface in dramatic and profound ways. This knowledge is not just academic. It gives us a window into the powerful forces that shape our cosmic neighborhood, reminding us of the dynamic and interconnected nature of our solar system.